Welcome back to Bielik Anatomy. I'm Kuba, and in the last episode we talked about the Bielik architecture and why I choose Triton for this project. Today I want to dive into something really fundamental, matrix multiplication. And I know what you are thinking. MatMul, really? But trust me, this operation is absolutely everywhere, and if you don't optimize it properly, nothing else will matter. In Bielik, we have a lot of them in every single forward pass. So today, I want to show you how MatMul actually works on the GPU, how we can write our own kernel in Triton, and what tricks we can use to make it fast. Let's start with a basic MatMul kernel in Triton. Here is a key idea. When we multiply matrices A and B to get C, we break C into blocks. Each GPU program computes one block of C. Let me walk through the code. First, we figure out which block we are responsible for. Next, we compute the offsets, the actual indices we need to access. This code gives us a range of indices. Now here is a really clever part, computing the actual memory pointers. We use broadcasting to create a 2D array of pointers. The strides tell us how to step through memory. Then comes the critical part, the K-loop. We can't load the entire row of A and column B at once because they are too big. So we process them in chunks. Now here is something important, the masks. What if our matrix dimensions don't divide evenly by the block size? Say M is 100 but block M is 64. The last block would try to access rows 64 through 127, but rows from 100 to 127 don't exist. That's where masks come in. The mask is a Boolean array, same shape as our tile, that's true for valid elements and false for out of bounds. Without masking, we either crash from invalid memory access or get garbage values in our result. And that's it. That's a working MatMul kernel. It's time for the first benchmark with PyTorch on my GPU. To do this, let's run benchmark script. Our implementation is about 2 times slower. But don't worry, there is still room for improvement. The bottleneck is memory bandwidth and how we use memory hierarchy. Let me show you the GPU memory pyramid. At the top, we have registers, incredibly fast. Then shared memory, on chip, really fast. Below that is L2 cache, and at the bottom is global memory on your GPU RAM. The speed differences are huge. Global memory is many times slower than shared memory. The order in which blocks are processed matters for L2 cache hits. Basic implementation processed blocks row by row, block 00, 01, 02, and all the way across. But by the time we get back to a similar part of matrix B, the L2 cache has already evicted that data. The solution is grouped ordering. Instead of going row by row, we group 4 blocks together and process them as a superblock. This way, blocks that use similar parts of A and B run close together in the time, and we get more L2 cache hits. Let's compare row by row and grouped ordering implementation. In the optimized version, the code reorders the execution grid to process blocks in vertical groups, allowing the GPU to reuse cache data from matrix B multiple times before discarding it. Probably you have noticed that in the first implementation we have hard-coded block sizes for M, N, and K. The optimal block size depends on so many things: the matrix size, the GPU architecture, shared memory limits, register pressure. Searching optimal values for every combination would be nightmare, but Triton has auto-tuning mechanism. Triton compiles the kernel with each configuration, benchmarks them all, and picks the fastest one, automatically. To enable auto-tuning, we simply add the Triton Auto-Tune decorator to the kernel code. Alright, now for the big one. This is where the magic happens: Tensor Cores. These are specialized hardware units on modern NVIDIA GPUs that can do a 16 by 16 matrix multiplication in a single instruction. One instruction. This single optimization gives us more than all the others combined. To use them in Triton, I just need to switch from floating point 32 to floating point 16 or bfloat 16 and make sure block sizes are multiples of 16. And Triton automatically generates Tensor Core instructions. I don't have to write assembly or anything. Additionally, for numerical stability, we keep using floating point 32 for accumulator. The final touches are pipeline optimization. Modern GPUs can overlap memory loads with computation. By increasing the number of pipeline stages from 2 to 5, the compiler can hide memory latency better. I also increased the number of warps from 4 to 8 to improve GPU occupancy. We can apply configuration in Triton Decorator config. Let's run matrix multiplication benchmark for final implementation. We beat PyTorch for most matrix shapes, but for smaller ones we lose. Why? PyTorch calls cuBLAS, which has specialized kernels for every shape. When m equals 1, it switches to a completely different algorithm optimized for that case. Our kernel uses one generic approach for everything, wasting work on tiles filled mostly with zeros. But keep in mind, we achieved this with pure Triton, no external libraries, and we have full control over the kernel. We have learned a lot today. Memory caching is very important. Tensor Cores give us massive speedups if you are willing to use lower precision. And auto-tuning is your friend. If you are following along, the code will be on my GitHub. I encourage you to try this yourself. And if you discover something interesting, share it in the comments. I would love to hear what you find. Next episode, we are going to tackle RMS norm and softmax, another operations we can optimize with a custom kernels. And I'm excited to see if we can get similar speedups. Thanks for watching. If you are enjoying this series, hit subscribe button. See you in the next episode. Bye!